this week we're going to be doing a really classic problem in Phys 1. And that is a pulley that's pinned into a wall and has a block hanging from it. And our job, given the mass, the radius of the pulley, and the mass of the block, is going to be to find the acceleration of the block. So here's what we're going to do. I started by drawing a couple of free body diagrams. One for the pulley, an extended one for the pulley, and one just a regular free body diagram for the block. And so on the pulley, I've got the tension force pulling down here, and I've got a weight and a pin force. So the pin force is just the force holding it in, and since I have no clue which direction it's pointing, I drew it in a random direction. It doesn't matter so much in the context of this problem. For the mass, I've just got a tension pulling up and a weight pulling down, and that's it. So let's think about how we're going to use this. So I don't want to deal with maybe sum of forces on the pulley, because the pulley doesn't actually move, it just spins. A more useful thing would be to talk about torques on the pulley. And since I don't want to deal with this pin force or this weight force, I'm going to go ahead and put an axis right here at the center of the pulley. And I'm going to think maybe I'll sum my forces on here. Or sum my torques, sorry. So I've got to choose a positive direction. Maybe I'll just choose this way to be a positive way, clockwise, because that's the way that the tension pulls. And we see neither of these forces has a torque with the axis placed right here in the center. So if we sum our torques, it looks something like this. We've got tension in the rope, TBP, times the radius of the pulley, which we're given, and then I'll call it radius of pulley over here too. Tension times radius, and then we don't need a sine of any angle or anything like that because the tension and the displacement from the axis are already at right angles to each other. So that's our sum of torques. And that is going to equal I alpha. And in the case of this, I'm going to tell you it's a solid cylinder, and so it's a uniform cylinder. And so I can look up on my equation sheet, I is just 1/2 mass of pulley, radius of pulley squared. And maybe I'll call it mass of pulley over here too. So then this is times alpha, and we move on to our next part. We're getting close. What we want is A, and I know alpha is really similar to A, but I still don't know T. And so here's going to be the way I'm going to find that. I'm going to look at these two. I'm going to say, if this way is positive, I really want to keep everything consistent when I apply my rolling condition. So I'm just going to go ahead, so I don't have to worry about this later, and make downwards the positive direction. I think if the pulley spins this way, the mass will fall. So if this way is positive, down is positive. So then I sum my forces on the mass, and I end up with weight pulling down, and then tension pulling in a negative up direction. And those sum up to mass of the block times acceleration of the block. So now we're even closer. We've now got two equations. We're missing tension from each. So we don't know tension, we don't know alpha, and we don't know acceleration. And so our last equation, of course, to sort of bring this in and get three equations and three unknowns, is going to be the rolling condition. And so I know if something is just spinning and something else is just falling from it, then I can relate the acceleration of that thing falling to the angular acceleration of the thing spinning. And I know the condition looks something like alpha times r equals A. So in this case, that's just going to be alpha times radius of the pulley, because that's how far out the block is, equals acceleration of the block. So now I'm missing alpha and acceleration, but you can see everything I've underlined is an unknown, and there are only three distinct unknowns. So now I can just solve this system of three equations and three unknowns for A, and that would be our final answer. So I will leave that as an exercise to you, and we're done.